Hello friends, today we'll talk about atomic radius. As we are moving into the second lecture of periodic classification, now let's talk about the periodic properties. As we know that there are, with the help of electronic configuration, we came to know that there are periodicity, or what we can say the repetition in their outermost electrons. So same is the pattern we can observe with the properties. And what are these periodic properties? And before entering into the details, before entering into the knowledge of this modern periodic table, first of all, let's talk about the periodic properties. Today we'll talk about the very important periodic property, that is atomic radius. So now let's start. So guys, today we'll talk about atomic radius. Now, to calculate the atomic radius as such is pretty difficult for us. And why is it so? Just try to reconsider that definition. The atomic radius is the distance between the nucleus and the outermost electron. But we all know that just because of that uncertainty principle, we cannot be so certain about the boundaries of this atom. You cannot predict the exact location. So how can you find out the exact radius? Yes, right. And even if we try to calculate that, that is of the very minimum order, 10 raised to the power minus 10 sort of. So it's pretty difficult to calculate the atomic radius as such. So what we can do, we can find out the alternative methods to calculate this distance, to calculate which can be considered as an atomic radius. So now let's talk about the first type, and this is known as covalent radius. My dear student, covalent radius, as the name itself suggests, it has something to do with this covalent bond. Many of you are wondering, okay, what is this covalent bond, sir? And some of you may know this type of chemical bonding from your class 9th. If anyone is previously was taking that exams known as NTSC, and you can see the Science Olympiad. So in that case, you must have heard this term covalent bond or ionic bond. And rather, covalent bond as such is actually a sharing bond where two atoms combine together and share their electron to acquire the nearest noble gas configuration. Octet rule, okay? But soon we come to know that octet rule is not that much successful in explaining all the properties of a chemical bond. But for the time being, let's consider that sharing of electron takes place just to complete octet. So covalent bond is a sort of what you can say the sharing bond. So let's say two atoms like hydrogen, two atoms hydrogen like H2. We are talking about the molecules of H2. So we have this combination of H2. There are two atoms of hydrogen coming together, joined together. Okay, so they are actually forming this covalent bond. This is the line combining the nuclei of these two atoms. So what we can say and how we can find out this radius sort of concept. Just imagine if we calculate this distance and multiply it with 1/2, it can be considered as the radius of this atom, isn't it? My dear student, with the help of X-ray technique, we can actually get a picture of H2 molecule. And certainly half of the distance between these two combining nuclei can be considered as an atomic radius. Okay. So as we're taking a cube out of this covalent bonded situation, so this will be better known as a covalent radius. So how can we define the covalent radius? This is half of the distance between the two combining nuclei of a homoatomic. Both of these atoms must be same. Of a homoatomic molecule. Fine, my dear. So this can be one of the method. But not all bonds can be considered as a covalent bond. You must have this metallic bonding. You know that there will be ionic bonding. So now the next one is, the number one is covalent radius. The number two will be metallic radius. But we're going to follow the same principle. We're going to follow the same principle. As we know that metallic atoms, they combine together to form a pretty hard crystal lattice. And you definitely came to know about this term crystal lattice in your class 12th when we are going to study important topic known as solid state. But for the time being, when we are talking about this metallic radius, so metallic radius is again half of the distance between the two combining nuclei of these metallic atoms in a crystal. Half of the distance between two combining metal nuclei in a crystal. Fine. In addition to these two radius, we can say that the third one will be ionic radius. When we are going to discuss about this ionic radius, so now what can be the proper definition of this ionic radius? You may say, sir, okay, let's talk about NaCl. Fine, Na plus Cl minus. This is the very particular example of this ionic bonding. So my dear student, now you may get this sort of confusing idea that sir is talking about the covalent bond, sir is talking about the metallic bond, now he is talking about the ionic bond. How can we understand all these terms? Because we still to go through this chapter known as chemical bonding. Yeah, I agree, and I will not expect that you will be pretty thorough with all the properties of these bonds. But yes, you can consider that ionic bond is a give and take bond. What do you mean by give and take? Sodium is about to lose one electron and chlorine is going to get that electron. Give and take. Ionic bond. While losing an electron, sodium will acquire this positive charge, while chlorine become chloride by acquiring a negative charge. We know pretty well that opposite charges will attract. So sodium, this Na positive, and chloride, this Cl negative, will get attracted towards each other. And this is what an ionic bond is. Like when carbon and hydrogen, they form a compound known as CH4, then the 4 electrons in the outermost shells of carbon will be shared by 4 different hydrogen, and both of these can acquire a state of noble gas configuration. That is, they can complete their octet. This sharing is considered as a covalent bond. So give and take is an ionic bond, sharing is a covalent bond. Now, what next? How can we define an ionic radius? You may think, okay, sir, in the same way, we can take the half of the distance between these two combining ions. No, you cannot. Because you must remember that particular thing. Homoatomic. This is not homoatomic. This is not homoatomic. H2 is homoatomic, N2 is homoatomic, O2 is homoatomic, but Na plus Cl minus is not homoatomic. So we cannot say that this half of the distance can be taken as what? The ionic radius. But for sure, what we can say, the radius of the cation, that is of Na plus, it must be smaller than that of the neutral sodium atom. And why is it so? The neutral sodium atom will have this shell configuration of 281. The cationic sodium is 28. As it has lost this outermost electron, so we don't require the third shell anymore. So definitely the size will decrease. So size of the cation, size of the cation will be lesser than its neutral atom. In case of an anion, or you can say the anionic radius, when chloride ion is formed, the incoming electron will face some repulsion from the outermost electron. Why is it so? Just take this. Let's take an example of this. Chlorine is 287. If chlorine wants to, hold one extra electron, if it wants to carry one more electron in its outermost shell, then that electron must face heavy repulsion from the 7 electron already present in the vacant in the valence shell. In this valence shell, the incoming electron will face a huge repulsion from these 7 electrons. So the incoming electron will definitely, this is the nucleus of the chlorine. This is the first shell containing 2 electrons. This is the second containing 8. And finally 7. The incoming electron will assume a position just outside this outermost shell. It cannot come inside this valence shell because of this huge repulsion. It will assume a location or a position just outside, just a bit outer. So what we can say, that now Cl minus is bigger than Cl. So my dear students, size of the cation will be smaller than that of the neutral atom, and size of the anion, let's use this color. Size of the anion will be more than that of the neutral atom. Fine. These two you need to remember. Fine, my dear students. Now, how to compare? What type of problems you can face in your exams? Pretty easy. Variation in these properties. That means variation in radius. Okay. So when we talk about these radius, then we need to consider 2 factors. Number of shells is the first factor we need to consider. And then effective nuclear charge. What do you mean by this effective nuclear charge? In one of my video in this on this channel, I was talking about Slater's rule. Slater's rule, effective nuclear charge. What do you mean by this? It's pretty easy to understand. Let's say during one of our school picnics, we were there and organized one bonfire, campfire sort of a thing. So this is the place of this bonfire campfire. This is the first ring of a student. This is the second ring of a student. This is the third ring of a student. As we very well understand this concept, that the heat is absorbed by this first ring of a student is more than that of the heat absorbed by the second ring of the student. And the third ring will get a pretty minimum amount of heat from that fire. So as we are moving away from that fireplace, the heat equivalent is decreasing. Okay. So in the same way, the positive charge, let's say we're talking about a nucleus of sodium. We have 11 positive. That means 11 proton inside of the nucleus. The first shell will face somewhat this 11 positive. But what about the last shell electron? Will it what you can say, will experience that plus 11, the plus positive 11 of the charge? No, because in between these shells will definitely decrease that amount. So this effective nuclear charge may be represented as Z star, where this Z star is my effective nuclear charge. This Z is my atomic number, or what you can say the nuclear charge. This sigma is your screening constant. This is actually what you can say the equivalent to the absorbed charge of the inner shells. So this is what this outermost electron is experiencing. So number of shells and effective nuclear charge, these are the two factors which can affect the atomic size. So let's talk about when we move from top to bottom in our periodic table. It is known as down the group. When we move from top to bottom, as we say, we can say down the group, then the number of shells keeps on adding. You must have this idea that we have this 7 periods and 18 groups. So these horizontal things, these are periods. So these are actually 7 shells. Fine. So as we move down the group, number of shells keeps on adding. And as number of shells keeps on adding, the atomic size definitely increases. Okay. So what we can say, these radius will increase. So what you can say, that potassium will be bigger than sodium as the first group is. This is Lena, Kabr se Farar. Francium is my radioactive element. So my dear students, as we move down the group, atomic size will increase. Okay. And from left to right, it is also known as along the period. Along the period, the shell will remain same, but number of protons inside the nucleus or number of electron inside that shell will increase. This will amount to the greater attraction. Fine. That means as we move from left to right, number of protons in the nucleus will increase. Oh, very good. And number of electron in that particular shell, because as we know, the shell will remain same when we go from left to right. In that particular shell will increase. This will lead to greater attraction. Atomic size decreases. ठीक है जी. So atomic size decreases. This is the variation. One more pretty important aspect while comparing the ionic radius thing. How can you find out which one will be more, or which one will be less in size? So pretty important aspect. I'm going to note this with a red pen. To compare ionic radius of isoelectronic, you must have heard this term, isoelectronic, same number of electron, like Na plus, Mg2 plus, O2 2 minus, N3 minus. So more the number of negative charge, that means electrons will keep on adding outside the outermost shell. So more the negative, better the size. More the positive, lesser the size. So यहाँ पर in this case, what we can say, N3 minus is 10, O2 minus is 10, 10, 10. All will contain same number of electrons. These are isoelectronic species. So N3 minus, because it has the maximum negative charge, and then O2 minus, and then Na plus, smallest will be Mg2 plus. The another reason is in case of Mg2 plus, we have 12 proton and only 10 electrons. So that means that powerful nucleus will attract these electrons towards itself more than that of sodium, because sodium contains only 11 as compared to 12 proton in magnesium. Fine, my dear students. So this is how we can understand the concept of atomic radius, sizes, ionic radius, metallic radius, and finally, let's wind it up with one more type of radius, that is Van der Waals radius. Let me tell you, Mr. Van der Waals is a pretty important person in terms of knowing the intermolecular forces. So Van der Waals believe that there is something more than that of these combinations, like you and me. Let's say you and me are not related. We don't have this sort of blood relation. But yes, if we belong to same country and we went abroad for some work, and then suddenly you saw me and we met somewhere, and then what can be a sort of interaction? Oh, you are in Indian, so that force of you are what we can say you're a British. That means a same sort of, you're not related, you don't have that relationship, you're not no blood relation, no friendship, but there is an association. You belongs to same country. In the same way, let's say one H2 molecule, the another H2 molecule, we have one mole, because we will talk about in terms of we always talk about these substances in terms of mole. So when we talk about 1 mole of H2, then there can be a 6.022 10 raised to the power 23 molecules. So what is that interaction force that holds them together? Fine, 2H atoms are bounded by this covalent bond. I agree. But how this much number of H2 molecules are closely knit? What is that force? Now that force is known as intermolecular force. And Mr. Van der Waals will talk about this Van der Waals forces. We will discuss about these intermolecular forces very soon. So Van der Waals radius is half of the distance. It's half of the distance between two non-bonded nuclei of the neighboring molecules. Fine. So with this is the second lecture of periodic classification, and we discussed all types of radius and sizes and their variations. I hope you must practice this and learn this from your textbook also. But this is something we want to discuss, and this is in short everything about atomic radius and there is its variation. Okay, all the best. In my next lecture, we will discuss about ionization energy, pretty important topic. And if you want me to explain this effective nuclear charge in detail, and if you really want to discuss with me the Slater's rule, please leave a comment in the comment box. Thanks for sharing and liking this video. Take care, guys.